Thank you, Professor Tao. First of all, I would like to thank Professor Tao, Professor Jian for the invitation for this talk. Actually, I'm supposed at conference site, but unfortunately, I'm doing self-quarantine at Zhuhai. I haven't been in mainland for a pretty long time, actually. So my topic will be flexible batteries. Let me try my best to keep the time. That's let me think, 20, 40, 45, around. Okay, my topic will be flexible batteries. It has been many years that people work on flexible battery, a lot of demonstrations. But still, we have too many programs. Well, we don't see the commercialization of flexible batteries in large scale. I mean, small demonstration, there's a lot of them. So I'm going to demonstrate my research in this field. I also come up with some challenges. So first of all, when we talk about flexible batteries, so I would like to divide flexible battery to be so-called omnidirectional deformable batteries and unidirectional deformable batteries. The background is you have a battery, you want to make it flexible. That's it. Rigid structure batteries, like normal battery, if you're trying to make it deformable, it can be a flexible battery. The background is always come from wearable electronics, but wearable electronics sometimes is flexible electronics, sometimes it's not flexible. For example, you have a smartwatch. Smartwatch is not flexible at all. Well, we have in terms of electronics, we have flexible sensors, flexible circuits, flexible display, but the battery as one of the important components to power or the flexible electronics. Well, it is also very difficult because it has many layers. Sometimes you got to think about liquid sealed inside. And the awkward situation of flexible battery is even it is wearable electronics. Sometimes they don't need a flexible battery. They just put a piece of small batteries, button batteries, for example. It also works. But in the future, for example, if we have smart clothes, we have a lot of sensors equipped. We have data analysis. We have wireless transmission. We probably also have energy harvesting. You have a battery component for smart clothes. But if you think in details, the flexible batteries, let's say wearable batteries, it can be divided into at least two types of batteries. Because batteries, we have different technology to develop different batteries. And if you analyze wearable systems, they also have different requirements. For example, if you have a smart facial mask, if you have various monitoring clothes, ECG garment, for example, so this kind of device, they close contact with your body so that they can collect the sensor signals. So they have the requirements. For example, it should be ultimately safe, very safe. It should be comfortable, soft. It should be medically safe. But since this is like one function device, so probably they can accept relatively low energy density. So that is acceptable. We call this omnidirectional batteries. Ultimately, you can have very soft battery instead of just bendable. On the other hand, we may have some other requirements. For example, if you want to use flexible battery as smartwatch, the watch band, flexible phones, for example. So the requirement is high energy density because this kind of device is multifunctional. They have a lot of functions. They need a lot of energy to power. So they have to be high energy density. And the flexibility might be not, we don't need a very soft battery. We only need, for example, bendable battery. We call it unidirectional batteries. So at least we can have these two types of batteries. for different application scenarios. If you analyze our current battery technologies, probably for bendable batteries, I mean unidirectional batteries, that lithium battery will be the ultimate solution. If you go into the lithium-ion batteries, you will see that different systems has been developed for lithium batteries. But probably among all the materials, lithium cobalt oxide system together with graphite will be good enough because it has ultimate its highest energy density in terms of volume. So it should be the solution for the unidirectional deformable batteries. But lithium batteries generally use aluminum plastic film to pack. It's not that flexible. So if you want a lithium battery to be flexible, you got to do some structural design instead of trying to use very soft materials, because soft materials, even you use soft materials, the aluminum plastic film will be still not soft. In other sense, if you go for soft batteries, omnidirectional flexible batteries, we think that zinc-ion batteries can be a solution. It has a distant energy density. I'm not saying excellent. It has distant energy density. It uses aqueous electrolyte, which gives it very good safety performance. And it can be flexible because if you use water, the packaging materials can be soft as well. So you may have, for example, the hydrogel separator and hydrogel electrolyte packaging materials can be low requirements. You don't need aluminum plastic film. You can use softer materials, for example. Also, we have different systems. So I would like to talk about our research on zinc-ion batteries based on the flexible zinc-ion batteries. A few research topics. One is hydrogel electrolyte. Because it got to be a kind of polysolid state device. So you develop solid electrolyte or polysolid. Zinc battery is not a new technology. It's been quite old. Started from zinc manganese oxide, which is not rechargeable. But since the say last century, I say, so zinc manganese battery has been developed, and also people trying to make it to be rechargeable. For example, this one, they make it to be rechargeable, and it can be recharged for 100 times. But this is in liquid. So we're trying to make a kind of hydrogel with gelatin and PMA chains, two polymer chains. They have different functionality. Inject this hydrogel into a kind of PN-based membrane to get a piece of film that works as a separator and electrolyte. Well, you see these pores, they can store a large amount of water, which can conduct ions. If you sandwich this with the two pieces of electrode, you got a piece of battery. It can be very thin, can be very soft. But honestly speaking, if you make it very thin, the energy stored in these batteries is not that much. Okay, so this typically zinc manganese oxide battery charge curve, we can make it to be cycled for 1,000 times. It's pretty good in terms of energy density and power density. It's pretty good if you compare with other flex batteries. But we have some tricks here. If you make it very flexible, you will lose the energy density. If you lose the flexibility, you got energy density sort of trade-off like this. And it can be very safe. You can deform. You can also even burn it on fire, or you can wash it for certain minutes, for example. It can still power something. You can still power something. You can even sew it on the clothes, like a piece of clothes, fabric. I can cut it into different pieces, and then it can still work. Well, when you do all of this, you put it in on a very harsh condition that you do lose some capacity. For example, the capacity loss for bending test, for humming test a few times, you still get 90% of the battery capacity. If you put it on fire or just soaking, you lose more. But sort of if you put a drop water to the battery, for example, the electrolyte is dried out. If you put water in, that you can recover a little bit. However, the capacity retention is not bad actually. And it can demonstrate some applications. For example, we can use 4 pieces of batteries because this pulse sensor has 6 watts. You need 6 watts to power. And also you can use it to power smartwatch, but unfortunately in a few minutes. And this is smart ISO powered by 2 pieces of a battery. You can jump, you can run, do whatever to the battery. It's very, very tough actually. You don't have to worry about it. You can power this for a few hours. It can still work. Another concept I'm trying to incorporate into my flexible battery research is toughness. The toughness is a very general concept in the study of material study. But if we are talking about flexible devices, I mean, at the device level, it's supposed to be tough. Tough means the energy absorption ability, the ability to absorb enough amount of energy and do not feel well for device. But it is quite difficult actually. But if we really want our flexible device to be useful, the toughness of the device should be considered. We start from supercapacitors. While I don't think a supercapacitor, flexible supercapacitor, can be used for. It stores very limited amount of electricity and it will self-discharge over a area. So it's not useful, but it's much easier to demonstrate this kind of concepts that you can deform this battery into any chips, apply any deformations to the device, then it can still be alive, for example. To develop flexible batteries device, we start from super tough materials. That this kind of hydrogel, we incorporate 2 kind of cross links. One is covalent, the other one is our only cross links. So with this 2 kind of cross link, that you can have very tough. This is toughness. This is toughness, fracture energy. It's quite tough materials that you can see the force is much larger than the normal hydrogels, and the fracture energy is much higher. That tells you that it can absorb a lot of energy and will not feel. That hydrogel you can just cut from top to bottom, and you cannot just separate it into 2 pieces. It's not like self-healing, cut it into 2 pieces self-heal. It's not like this. You cannot even separate because it can absorb a lot of energy. So you can put it into 2 pieces of electrode conductive materials and press to alternate. Then these 2 parts will be still separated. That means it can be used as electrolyte, core solid state electrolyte and separator. Can be very tough. And you can also use this hydrogel to protect the bare electrode. For example, this one you cut without the coating of the hydrogel. If you coat it with gelatin, it's improved. Say the number increased to 700 grams. Okay, right? Then we stop. We'll shortcut it. Then, okay, if you cut it with our hydrogel, the number of you can keep increase the number to 5 kilograms. But still can well protect the electrode. Then you can have this device. On the different deformations, you will see the charge curve. There's no fluctuation. You can still say very stable charge-discharge curve. But this is simple passive. This is not that difficult. And you can even put the piece of device on foot, step on it for 3 days, then for another 3 days, put it on road with a car to run over. Then you still have the overlap charge-discharge curve and CV curves. You can still use it to power something. I mean, I don't feel this one will be, I mean, very useful, but the super tough device, the concept will be good. We also apply this to zinc manganese batteries, for example. We can also do anything to this device that to demonstrate the very good toughness. But honestly speaking, we do find more and more problems in the flexible battery devices. That's an issue. That's a previously we're trying to improve the energy performance, and we're trying to make it very tough. Then, well, if you think about all of this seriously, you got more and more problems. Okay, that's research. For example, we've done a lot of things. Sorry, how to? Okay, we've done a lot of things. Dendrites, because zinc-ion battery typically we use zinc metal as anode. Zinc metal, when you do the stripping plating, you have dendrites. You have dendrite growth on the surface, similar to the lithium metal anode. So this is a demonstration. If you start from a smooth surface and you do cycling a few cycles, you will see something like the surface will get much rougher, and the zinc dendrites kept growing up. So if you have these dendrites issues, you can think about a flexible device. You can think about a flexible device. For example, if you follow the flexible device with a piece of zinc at the folding area, the dendrites will be more severe. For this is a study. Like if you don't fold, you can do planar test. It's around 100 times cycling. You can do it. But if you fold it, for example, at this age, it's easily got short circuit. That you can have short circuit easily. If you look through these pieces of area, so you have larger and larger dendrites, larger, getting rougher and rougher in this direction. So, and if you see the R, the diameter of the folding, then definitely with smaller from 10 to 2, that the cycling life is getting also getting shorter and shorter. So so that means if you make it flexible, you got a problem. So we're trying to solve this problem. We're trying to make a flexible battery to be free of dendrites. Then we use the very powerful electrolyte. It's called highly concentrated salt electrolyte. It's used. It was reported, and we also verify that in this kind of electrolyte, generally there will be no dendrites. But put it on in the flexible configuration, we still have got a lot of dendrites. You will see that if you fold, for example, the blue line, they're very short cycling life. And if you put it, for example, 10 R is larger and longer life. You have this kind of dependence, and you can see at the folding age, you got a lot of roughness here. The reason is quite simple. The reason is quite simple, that you have the accumulation, the high electric field around this area, and also you have sliding, because, for example, you have hydrogel, even you have hydrogel electrolyte here. When you do bending, that you have this kind of sliding, slippery, induced by interfacial conducting, because the interface, the binding force might be not that strong, that can have slippery. That also induce the dendrites growth. So ideally, that this one we cannot control. The accumulation, the high electric field that we cannot control. If you have deformation, you have this enhanced electric field. But this one we can control. And if we want to prevent the dendrite growth we have, what we can do is to use a very strong electrolyte. I mean, mechanically, to prevent, to block the growth of the dendrites. So that's we design this kind of highly concentrated salt hydrogel. It's quite tough. You see this one compared with the normal hydrogel here. So this one is much better in terms of the force. I mean, it's much stronger. If you apply this one, generally, you don't see very much dependency between the R and the dendrites and the cycling lives. So they can be partially soft, but physically will be still there. Okay, a second part will be bendable. It goes for lithium batteries. If it goes for lithium battery, we're not the first one. For example, Professor Chen developed this kind of biomimetic design that to simulate the backbone of to mimic the backbone to get some flexibility. For example, this one. But we studied all the kind of structures of the batteries. We use some simulation. If you see, this is we use the copper foil to demonstrate the bending. Copper foil is a current collector in lithium batteries, and gray color here means malfunction. So if we simulate this kind of structure, the problem is when you bend a little bit, the battery can work very well. If you bend a little bit, it can work well. If you fold it, if you're trying to fold it, then you got a malfunction here. Here is high stressful area. I got a lot of problem. That's because of this kind of structure. So we're trying to mimic this kind of structure with a kind of articular surface ligaments, so that this kind of two surfaces can separate and the deformation can be large. So you could eventually we design the any storage unit to have this kind of surface, and we can also use similar technology to develop a battery with different structure and storage units. For example, this one, they have different. For example, they have different deformability. For example, this one, they can be stretchable, sort of stretchable. So this one, it can give you another deformability. And we mimic, we do simulation for the stress distribution. You do have some different stress distribution here, but even you fold it, if you fold it or twist it here, if you fold it, you don't have malfunction part. If you twist it, it cannot be very large, but it can still sustain some twisting. And if you have different any storage units, for example, you still have this kind of folding, twisting ability. Well, this is redesigning coating pattern and staking models, and we can make a lot of them. So we do different tests, for example, bending test, for example, here for different structures that you have very stable capacity retention and overlapped Chunyi curve. If you do bending for even 200,000 times, that within the 17 cycles, that the capacity retention will be still good, and also twisting here 25,000 times. You do lose some capacity, but the capacity retention is not bad. If you change it to be this kind of structure, it can be stretchable. It can be stretchable, and we also do a lot of demonstration. For example, you use our battery here. We can use our battery here to power earphone. We can use our battery to make the smartwatch to work like 22 days, and also some other devices. Okay, but honestly speaking, we still have some challenges. Although when we do the binding test, when we do the when we do the twisting test, we all pass all these tests. It seems that we have all of them. But problem is when we fabricated, for example, 100 batteries, we found that some of them on the deformations, they may have some gas after a certain period, for example, 30 days. Within 2 days, 3 days, it will be fine. But 30 days or a few months, you will see more batteries get gas coming out. So still some battery, we guess that the SEI film is broken in this case. We are trying to develop tough SEI films in our lab, but it's much more difficult actually. Okay, that's I think I can skip this, but I still have 1 minute to. I'm another editor-in-chief of Nano Research Energy, which is created by Tsinghua Press, and we have international editorial board, and we target on very high level journal on the nano materials and technology for energy storage conversion, and also as demonstrated by Professor Xu that we're trying to cover a wider spectrum of energy studies. Okay, that's my acknowledgement. Thank you.
Thank you. We have a question, online question. How the flexible battery is still functional after cutting it in different sizes? What is the reason behind it?
Yeah, okay, that's a kind of current solid state zinc-ion batteries with the electrolyte as is the hydrogel. That when you cut it, the hydrogel will not flow away. The liquid is not coming out because this gel stays. You still have the two electrolytes. You still have electrolyte. They can still work for a few, say, hours, but the packaging material is broken. So eventually the water will be evaporated away. That will not work anymore. But we're trying to demonstrate that even it's broken. I mean, for this kind of battery, because it's close contact with your skin, we're trying to demonstrate that when even it's broken, it will be still safe. It can still work for a few minutes. It's not important anymore because it's already broken, right? But it is safe. You don't have to worry about safety for this kind of batteries. Thank you.